So recall, when a is greater than 0, the parabola opens upward. This implies that the graph will have a minimum. Again, if your graph opens upward, then your vertex down here is going to be the minimum of your graph. If the parabola opens downward, the graph will have a maximum at the vertex. Right? So if I open downward, my vertex up here is going to be the maximum or the highest point on my graph. Let's look at exercise 13. A rancher is fencing a rectangular area for cattle using a straight portion of a river as one side of the rectangle. If the rancher has 1,800 feet of fence, find the dimensions of the rectangle that give the maximum area for the cattle. Well, the setup here seems like I'm going to have some fencing. But I only need 3 sides because that back side is going to be a river. Water. And you're assuming that the cattle are not going to walk into the river. Okay, so we have basically, like, I'm going to say grass over here with 3 sides of the fence, and then we have the river being one side of our enclosed area. Okay, so when I look at this, I think of area and perimeter. Area because it literally asked for area, and then perimeter because I'm basically counting sides. So I'm going to think of this as width, and length. I don't need length over here because I don't have fencing on the back because it's a river. Okay, so the 2 formulas I know are area is length times width, and I know perimeter, which is where you just add up all the sides. So for us, that's going to be a width plus a length plus a width. Now, I also know how much fencing I get to use, which is 1,800 feet. The fencing, or the 1,800 feet, is going to give me my perimeter. So I'm going to change my formula a little bit for perimeter to say 1,800 equals W plus L plus W, or simplifying even further, 1,800 equals 2W plus L. If I add up how much fencing I need for each of my widths and the fencing I need for the length, it should add up to the total fencing I have. Well, I can utilize this equation here to come up with a relationship between L and W so that I can go utilize my area formula. What I'm going to do is I'm going to solve for L. So if I subtract 2W to both sides, I end up with 1,800 minus 2W equals L. Okay, so now I'm going to substitute that into my area formula. So the area is equal to length times width, or area is equal to length. My length is 1,800 minus 2L. I'm sorry, 1,800 minus 2W. And my width is just W. Now let's multiply this out. So I have area equals 1,800 W minus 2W squared. Well, this power of 2 tells me that what I have here is a quadratic. I can think of this as a function a of w, so w is like my x value, and the highest power of x I have is 2, which means that this is a parabola. If I rewrite and rearrange the order, maybe now it'll look even more like our normal quadratic function. Now, if this is a quadratic, I can identify a to be -2. And when my a is negative, that implies that my parabola opens downward, or that it has a maximum at the vertex. So this function will be maximized at whatever value of x is our vertex. And we were asked to find the maximum area. So if I can figure out what value of x, or in this case w, is the coordinate of my vertex, then I can figure out what the dimensions of w and L need to be. All right, so we're going to use -b over 2a. Well, my b is 1800, so I have -1800 over 2 times -2, that's my a. The negative is going to go away, so I'm going to be left with 1800 over 4. And if you divide that, you get 450. Now remember, when we're talking about a vertex, we usually have x comma y. But I'm using w as my x's, so I'm going to think of this value I just got here as my width. So this is the length of fencing I need for my width to maximize that enclosed area. And now if I want to find my length, I just need to plug in 450 into this equation up here. So I have 1800 minus 2 times w. And remember, this is going to give me my length. Well, my w is 450. Well, 2 times 450 is 900. So the length that I need is 900. So I'm going to get my maximized area when my dimensions are 450 feet by 900 feet. Projectile motion. A projectile is an object that rises and falls under the influence of gravity. And projectile motion is the height of that object as a function of time. Projectile motion can be modeled by a quadratic function. The quadratic function that models this is s of t equals -16t squared plus v naught times t plus h naught, where s is the height of the object above the ground in feet after t seconds, h naught is the initial height, v naught is the initial vertical velocity in feet per second. If the initial velocity is upward, then v naught is positive, and if the initial velocity is downward, then v naught is negative. I call these naught, you can think sub-zero, but that's just like common terminology to say v naught, h naught. All right, exercise 4. A baseball is hit straight up with an initial velocity of 96 feet per second and leaves the bat with an initial height of 2 feet. Write a formula, S of t, that models the height of the baseball after t seconds. All right, well, we have the formula for projectile motion, right? It's S of t equals -16t squared plus v naught times t plus h naught. And we were given our v naught as well as our h naught. So we'll just plug those in. So our formula that models this situation is S of t equals negative 16t squared plus 96t plus 2. How high is the baseball after 2 seconds? Well, remember t stands for time in seconds. So all this is saying is plug in 2 for t, and it'll give you the height. Take a second to evaluate that and then come back and check your work. And you should have got 130 feet for the height of the baseball after 2 seconds. Find the maximum height of the baseball. The function we have here, S of t, is quadratic, right? We have negative 16t squared plus 96t plus 2. It also is opening downward. And this is a real life scenario. So we have some baseball player who's going to hit the ball at a height of 2 feet. The ball's going to go up, but then gravity is going to bring the ball back down. Right? So the maximum height that we're going to have of this baseball, think of this as a parabola, is going to happen up here at the vertex. Down here I have my t coordinate, which is the time. But over here where I normally have y, I have my s of t, which is the height. I want to find the maximum height. So I don't just want to find the x value or the negative b over 2a. I want to figure out the y value. So when I plug negative b over 2a back into my function. All right, so negative b over 2a, well, our b is 96. So negative 96 over 2 times our a, which is negative 16. Again, the negatives are going to go away. And I get 3. Now for us, our x's are t's, so these are seconds. I wasn't asked to find at what time is the baseball at its height, though. I was asked to find what is the maximum height. So I need to plug that in. So s of 3. So the maximum height happens at 146 feet, which is at 3 seconds. Now we're asked to estimate the domain and the range. So I just kind of drew like a really quick sketch over here of what the graph might look like, but we could try to graph this. I'm going to utilize a website called Desmos. All right, so we have negative 16 x squared. I'm just going to use x because we most commonly use x and y, plus 96x plus 2. Now, the way that I have my coordinates set up right now is that my y's are going by 2's, but you even saw while we were doing the math that our max height happens at like 150 almost. So I'm going to change the range of my y-axis to go from negative 2 to 150. And at least now I can see the entire graph. Actually, I'm going to spread it out a little bit more so I can see more things happening. Maybe I'll go to like 180. My x's seem to be okay because I can see just looking at this graph right here, it looks kind of like around 6 seconds is where the ball is going to hit the floor again. So let me zoom in. It does look like right here that our domain is going to end really close to x equals 6. And actually it's just a little bit past that, 6.021. And if I go back to the beginning of my graph, for our domain, we only care about second 0 all the way up till the ball comes back to the ground, which is really close to 6. So if I was going to estimate what our domain is, I would say that our domain is from 0 to 6. So from 0 seconds up to 6 seconds. We want to do the same thing for the range. Now, you can actually figure out the range even from this kind of cruddy graph that I drew up here, because I know the highest point it's going to reach, which is 146, and I know at some point it's going to hit the ground, which is 0. So my range goes from 0 to 146. All right, that's the end of 3.1, which was kind of an introduction to the quadratic function. In section 2, we'll go over quadratic equations and problem solving. Remember, if you need any additional help, feel free to send me an email and we can have kind of like an office hour together where we can go over these things some more. All right, I'll see you in the next video.